Hello, this is Richard Burton back to you from Hand Tools, and today we're going to be looking at Chapter 14, which is Properties of Metals. And so we're going to kind of give you some understandings of some different types of metals and some of the characteristics of metals in this chapter. So said it's very important for a maintenance specialist to understand the mechanical properties of metals, such as the hardness, the ductility, the malleability, the toughness, and the strength. It said these terms are the describe the behavior of metal in which is acted upon it with external forces. So as we know, metals are pretty much what all machines are built out of, because they're made to last and withstand a lot of abuse and to be able to hold up to a lot of pressures and forces being put against them. So we're going to talk a little bit about some of those forces and those terms. So hopefully once we get through this chapter, you'll understand a little bit more about how metal is made and how it's able to withstand what it can withstand. So the first thing it talks about, we're on page 199 in the textbook. It talks about hardness. So you hear hardness a lot when you're referring to metal. That is basically a term that's not too far from the name of it, is how hard is the metal. It says hardness is the ability for metal to resist penetration, and hardness resist denting or scratching. So in most cases, if you take any kind of metal, especially this is a piece of copper tubing, of course this is a file. If you take a file and take it across a piece of copper tubing, of course you can scratch the copper tubing really easy, which means that this is not very hard, right? So copper is a metal that's known to be very soft. Another metal that would be considered very soft would be a piece of aluminum. So if I take a file and rub it across this aluminum, of course I can feel it, scratch it, and dig into it, and I could shape it very easily with a file. So aluminum is still another material that is considered soft when it comes to hardness. And then if you take a regular piece of steel with no special chemistry to it, a regular piece of steel, I can put a file to it and I can scratch it and it removes the material very easy. So even though this is steel, it's still considered a softer steel than other steels, because the file is also made out of steel, but it's made out of something called tool steel, which means that the recipe of that metal has been changed when it's in its alloying content, and once it comes out, it goes through some changes. It has a certain amount of carbon in it, which the carbon, of course, we talked about earlier as being the same mixture that makes up diamonds. So that carbon content goes into the metal during the alloying when it's melted down. And once it comes out, it's gone through a process to harden it and make this metal strong enough to cut most other metals. So tool steel would be what the metal would be called that the file is made out of. So another thing it talks about is a test that can be done on metal to determine its hardness is basically what we just did, running a file over it. So it says when the files cannot cut the metal, that particular metal is considered file hardened steel. So I've got actually right here in my hand a carbide cutter that we would use on a milling machine. And when I try to file on this, the file just basically skates across it. It doesn't make any change to the outside of this material, because this material here is actually harder than the file and the steel the file is made out of. So the file doesn't do anything to this. In fact, it's literally, you can kind of hear the sound of it. It just sounds like it's skating across the top of it. It's not doing anything to that metal at all. You can't even tell where I touched it with the file. And if you could be standing here doing this yourself, you know exactly what I was talking about. So there's other metals other than tungsten carbide that's extremely hard. You know, not hard enough for the file to cut it. It could be something like another piece of tool steel that's just as hard as the file, and it would not be able to file or cut across it. Same as a knife blade. You know, knife blades are considered hard. If I filed across this, I probably would get some effect on the metal, because this metal is really thin where the edge is, so you can sharpen it. But most of the time when you sharpen a knife, you have to use something like a ceramic stone or some kind of hardened piece of grinding rock or something like that, a whetstone or something that will actually cut this metal and smooth it down and give you that edge again when you're sharpening something. It says various methods of heat treatment may increase or decrease the hardness of metals. Hardenability is the ability for metal to be hardened by heat treatment. Another term it talks about is brittleness. You know, like we talk about something being brittle. Most of the time when you think about something that's brittle, the glass comes to mind. You know, if you take a regular drinking glass and you drop it on a concrete floor, what's probably going to happen? It's going to shatter. Because even though glass is really hard, it's also brittle. So brittleness is related to hardness. It says the metal is said to be brittle when it cracks or breaks without much deformation. In general, the harder the metal, the more brittle. So it's like I think I told you before about a file. Even though a file is a thick piece of steel, if you tried to put this file under a lot of pressure, like to pry up on something with it, when you try to deform this file, which means bend it, if you bend it so far out of shape, instead of it bending like a piece of regular steel would bend, it would just snap. And that's because this metal is so hard, it's got a certain brittleness to it. So it would just break. If you've ever tried to take a file and use it for anything other than filing, like pry a can open or pry open a lid on a wooden box or whatever, you've probably broken a file because they do not take being bent very well. They'll just snap. Another word it talks about is ductility. Ductility is the ability for metal to be stretched into thin wire without breaking. It says copper and aluminum and soft steels are ductile, which can be drawn or pulled and to very thin wires without breaking. So another thing, this is a piece of Romex. When you think about ductility, you think about something that can be stretched down. Wire is probably one of those things that gets stretched down. Another thing that you think about with ductility is the fact that you can bend that wire over and it bends without breaking. So there's a little bit of ability for that ductility there, that you can bend that wire over and it doesn't like fatigue it and cause it to break. So that can be bent into shapes in many different ways, and it doesn't affect the strength of the wire whatsoever. Another word it talks about is malleability. Malleability is the ability for metal to be hammered into a thin sheet. So you can hammer it into a thin sheet of metal, and it says, for example, lead is a malleable but not strong enough to be stretched very, very far before breaking. Another characteristic or property of metal would be toughness. Toughness is the ability for metal to stand sudden shocks or high impact forces without fracturing or breaking. So if you think about toughness, think about something that would be made strong enough to take shock. What about the head of a hammer? So this hammer would be able to withstand pounding on something else without cracking and breaking. So that would be a good example of toughness. The next one it talks about is strength. So it's very important, you know, when you build a structure, especially like a tall building, you think about these large buildings, the structures are built out of I-beam. So they have to have a certain amount of strength involved in those. So it says strength is the ability for the metal to resist deformation, which means it won't bend, it won't flex or give or take on too much pressure that it basically just gives up its form. You know, it's taking a different shape. So testing is performed by deforming a sample of material and measuring the amount of force with the sample of resisting deformation. Okay, so it shows deformation on page 202, 14-3, and it shows different ways that you can deform metal. One way is through tension, which will be putting a lot of pressure on it, like it shows a picture of two people actually taking a piece of metal and pulling on it from both directions, so that would be tension. So think about when you build a building, all the tension that's brought on the walls from holding it together and things like that. Another one will be compression. So now you've got a piece of metal and now you're putting force down on top of it. How much can that piece of metal take before it gives up in the middle and bends? And then the last would be shear. So how much force can this metal take if something's pushing up on this side and pulling down on that side? Can it withstand the pressure being sheared in two? So that will be your three ways. It would be tension, compression, and shear. It says the amount of force an object exerts divided by the cross-sectional area is called stress. The maximum amount of stress of a material can exert what is called yield strength. So some way to be able to determine the strength of a piece of material is through a test. And so in order to be able to figure out tensile strength, it says the force which the metal resists by being pulled apart is called tensile force. And so if you look at tensile force, it says tensile force is equal to the force divided by the area. And they have determined that they have what they call a number that gives you the cross-sectional area as 0.200, which is 200 thousandths of an inch squared, which would be a constant that would go into that formula for area. So any force, which would be in pounds, divided by that constant, a 0.200 thousandths of inch squared, would give you tensile strength. So another thing it talks about is elasticity. And you're thinking elasticity, you're thinking about elastic. All right, so how can metal be like elastic? You know, you think about elastic in clothes, like elastic on a jacket's wristbands, or you stretch it and it goes right back, right? Well, what about elastic as far as a spring goes? You know, we use springs for almost everything, especially in machinery. And what we do with a spring is we take it, we hold it on one side with something, and then something else moves it and it stretches. But what happens when the force is released on it? It goes right back to where it was naturally at. So that's elasticity. It allows for you to be able to stretch the metal, and when you release it from the force, it goes back to its natural state. So elasticity is the ability to be deformed body to regain its original dimensions. Another thing it talks about is metal fatigue. So we've known if we do anything too much, we get fatigued, right? If we actually go and work out in the gym, we work out our muscles for a good while, our muscles begin to get fatigued, which means they lose their ability to have strength anymore. So we have to let them rest, right? Well, metal's a little bit different. If metal gets fatigued, meaning it's a process of over and over and over and over and over and over and over of the same abuse, eventually fatigue will set in. And he said repeated loads in machines causes failures of both ductile and brittle metals. Tiny cracks form within the metal as the strain changes. The cracks grow and join together. When enough cracks have joined together, the metal breaks. This process is called metal fatigue. So eventually, if you just go back and forth on a piece of metal that can't handle that much fatiguing, eventually it will break. And you see this a lot in like electrical connectors, cables on devices on the machine that moves back and forth. You know, once they move back and forth, say 1,000 or 100,000 times, that wire will eventually get to the point where the connection breaks inside the cable, and then the switch or the sensor quits working, and you're like, why is the sensor not working? Because the cable connector's broke. The power is no longer going to the sensor. So now the sensor's not working. So now the machine doesn't know why this part is not showing up with being located with a sensor. And so, of course, your machine stops off and is waiting for the sensor to start working again. And ultimately, you have to replace the connector or either the whole cable if it's a module or a molded connector and cable together. The next thing it talks about is thermal expansion and contraction. So we know that as metal heats up, it expands. When metal cools down, it contracts. So you have enough expansion and contraction that can also make fatigue happen. So fatigue can also happen from expansion and contraction. A lot of times that's how welding or welded joints break, from expansion and contraction over time of heating up and cooling down. I missed something here. Okay, one more thing I wanted to mention before we move on is whenever metals fatigue under high temperature, also talking about expansion and contraction, we'll think about something that's under high temperature, like the metal parts that's inside a furnace, that parts, maybe say the conveying that brings parts through a furnace to dry them or bake them or something like that. So those high temperatures are extremely slow and continuous and distort certain metals, which produces another type of failure called creep, which is CREEP. It says a high temperature makes the metal somewhat softer, and then it tends to very gradually respond to applied forces. So it'd be the same thing as if you took a torch and heated on a piece of metal long enough to soften it up, and it had a load on it, that load would then bend the metal out of shape. So it's the same process as that. The next thing it talks about is density. So we know that certain metals all have different densities. They all weigh different weights. So you can't never really determine what will be the best material to use on something that needs to be lightweight, but it still needs to be strong versus I'm not concerned about the weight, but I need something very strong. So a lot of times the weight has something to do with any device. It may be a fixture that's being picked up by or being lifted by a motor, and that fixture needs to be made out of something lightweight that can still be strong enough to hold whatever is on the fixture, but still be light enough that the motor can pick it up without straining or overloading the motor and causing a failure on that side of it. So let's look at something about density here. It is often said that steel is heavier than aluminum. This is an inaccurate statement unless the volumes are equal. A given volume of steel is heavier than the same volume of aluminum. When you discuss weight, remember that size does not necessarily indicate the weight of the object. The volume is the determining factor. In order to avoid problems caused by the differences in gravity, scientists compare the objects on a basis of mass rather than weight. Mass is the measure of how much material is in an object. It always remains the same no matter how gravity changes. Another thing it talks about is density. Density is the mass of the material per unit of volume. To calculate density, you divide the mass of the object by its volume. So right here, there's a formula. You see density is equal to mass divided by volume. When we were in the chapter on measurements, we talked about volume. Volume is a measurement in 3 dimensions. Length times width times height. So that's basically everything that is trapped into a object. So that's the volume of the object. And then it said mass is the measure of how much material is in the object. So if we want to know what the density is, we have to divide the mass by the volume, which is the size of it. A real quick note about what they were talking about as far as items being with density. These 3 items right here being piece of regular bar steel, a piece of aluminum bar, this solid, all this is solid, and then a piece of carbide, which is a carbide cutter. All three of these items here that I'm holding in my hand all weigh exactly the same weight. And you can tell by the weight that there's a big difference in the actual size or volume of these materials, because this is very dense, it's very heavy, so it's small but very heavy. This is the next thing, it's larger than this and still heavy somewhat. This is large but very lightweight compared to the carbide and the steel. So that makes kind of gives you an illustration of how density can affect the differences in objects. The last thing it talks about is called specific gravity. And it says specific gravity is a ratio between the density of a given material and the density of water. So we use water to compare everything to that, so we know what the specific gravity is of that. If you look on page 212, there is a table 4-14 about specific gravity, and it also tells you that certain metals and their specific gravity, if you ever wanted to know that for any reason. And then it also says if you wanted to calculate specific gravity equals the density of the material divided by the density of water. And so probably wouldn't be that hard to Google that information if you really needed to know that for whatever purpose. You know, maybe you decide one day you want to be a metallurgist, and the metallurgist, they have to know all the specifics about all kind of metals, and that information will be very useful if you're in some type of engineering and designing. And if you think about the reason that a lot of aluminum and titanium and magnesium is used on an airplane is because it's extremely strong, but also very light. So something that's got to fly in the air has got to be very light, but still has to be strong enough to handle all the forces and pressures exerted on it while it's flying and being pulled all around in the air and turn and hold the amount of weight of the people that's riding inside of it. One other quick thing that I wanted to mention is I know some of you are still trying to get your textbooks. So hopefully this video will be enough for you to do your homework questions. I understand that the books are on order and it's taking a little while longer to get them. We don't have a whole lot more time left in this this part of the semester, the lecture part of the semester. So hopefully you'll get those books in by this week, and they will be able to help you for the next few weeks that we got left. And but if you do know another student that you have their contacts and they have a book, maybe you want to reach out to them and ask them maybe to take some pictures of the chapters that you're going through right now, so you can have that information while you're waiting on your book. Or if for any reason you're trying to get a book, and I know the order is only going to probably go through this week to order those books. So if you're trying to get a book and you need financial help, there is ways to get financial help if that's something that maybe is preventing you from getting your book. But we only have a short amount of time for you to get in touch with me and let me know that may be the case why you haven't got a book. And I can try to get you in touch with someone and get that book ordered before the deadline. He sent an email out about a deadline probably sometime this week on that, because like I said, the semester is going to be ending for us pretty soon, and there really won't be a point to wait to the end of the semester or the end of the first part of this semester where we're going to stop using the textbook to order and get a book in. So any of those options that are out there for you to use, try to do what you got to do so you can get this knowledge or this information in your hands, or be able to use it to do your questions and also use on your test. Other than that, I am done for this chapter, and we'll see you on the next one.